Before we begin, just a note on the practical assignment. Practicals will be marked by 12 p.m. on a Wednesday, so that you have some time to review your mark sheet. And then if you have a query, you can direct message your marking assistant during the first period of the practical session each week. So that will be TH8, the eighth period on a Thursday. They'll be online on our Discord server, and you can direct message them. To know who your marking assistant was, we will add your assigned marking assistant as a mark field on Eve. So you'll just see the name of your assistant there, and you can contact them should you need to. Just note about this specific prac. I did see that some of you chose to use a separate data structure to sort your items. Some of you used a map. I assume this is because you looked forward in the textbook where there's a similar exercise where you have to sort words based on frequency. Of course, you won't get marks for that. You're not supposed to use a different data structure to the one that we're doing a practical assignment on. And in fact, you use the map, which should not have, which requires the use of unique keys, and frequencies are not unique. So that is incorrect. I will state this explicitly during our practical session, because it seems that some of you have assumed that you may use other data structures to do the work, which defeats the purpose of the practical. You should be using the data structure that you are allowed to. In this case, that was an array. And in the next pracs, or in every prac really, you're allowed to use Java intrinsics. So those are your primitive types, your enum, strings, arrays, but really no other data structures to do the work of the practical. And certainly sorting was the main work of that particular practical. So if you took the objects that you created, that type that was given for you, and you put that into another data structure to do the work, and simply called some method the data structure, then that defeats the purpose. Certainly sorting, searching, and other methods are trivial when we're using trees like a map, but we will get to that. The entire idea is that we will see that there are efficient ways to do things and inefficient ways to do things. And as the need arises, we look at more and more complex data structures, but we will get to that. All right, so for today, we're going to be discussing, all right, we already have a question before we get started. What topic will be this week's practical, or this week's practical will be based on? That will be linked lists, which we'll be discussing today. So we will begin with arrays, which we're comfortable with, but which is a type of implementation of a list, and then talk about the more abstract idea of a list ADT, abstract data type. Then we'll look at some concrete data structures that could be used to implement a list. Another question, will there be a discussion on how each week's practical was meant to be done? No, you are supposed to use the data structure that we're discussing to implement this, but how you implement it is up to you. We make it fine-grained enough that there's really any way you can figure out to do the task of each method is fine. There is no one way that you're supposed to do it. Right? The idea is that you're supposed to become accustomed to problem solving by finding your own approach to doing it. And we give you a structure that's close enough, or rather that's closed enough that whichever way you do it will still work within that program. Will there be a memo? No, there won't be a memo for each prac. All right, so this is simply an outline of what we'll be discussing. As I said, it's mostly singly and doubly linked lists, so different types of linked lists. We'll discuss arrays just before that. Then we'll move on to recursion for the latter part, which will probably be in tomorrow's lecture. So arrays, right? You should be comfortable with these. You've made use of them in previous years. As I said before, we often have to save multiple elements of the same type. And so an array is a very useful way to do so. And so most, if not all, high-level languages allow us to be able to save multiple elements of the same type within an array. So the example that's given in the text is that of a game entry. So I wouldn't imagine that all of you have been to a game arcade, but if you had, you'll see that most games have a top score list, which is simply a list of names of people who've gotten the top score and their scores for each of those. Right, and so we'd want to keep an ordered list of scores to be able to say, well, these are the top 5 or top 10 scores that have been achieved in this particular game. And so within that, would have to be able to insert new high scores if someone gets a higher score than the current high scores, and remove one if we find that perhaps that person cheated or we simply want to remove one of those scores. And what we find is that although in Java we're able to leave cells empty, or that we can think of empty, even though they're initialized to whatever the default value is. So that'll be 0 for most of our primitive numbers or false for a Boolean. So even though our array elements all initialize the default values, if we're actually keeping meaningful elements within an array, we should not leave any spaces in there, right? And in fact, it goes against the very definition of an index for us to do that. An index is defined as the number of elements that appear before a particular element. So if you talk about the 0th element in an array, the element is with index 0, that means that 0 elements occur before it. And that's true. If we go to index 0, that'll be the first element in our array. If we go to index 1, that means there's 1 element that appears before that particular element. Index 10 should have 10 elements that appear before it. If we then allow there to be spaces between them, then we destroy that definition of an index. And also, well, then what happens? We try to traverse that array and do operations on things that have not been initialized. Sure, in Java, they'll be initialized if they're primitives to 0 or false, and null if it's a reference type. However, that's not true of every high-level language. In fact, in C++, you'd find that it leaves whatever garbage was in there to begin with. It could run into some serious issues. So each time that we add a score into our array or remove one, we're going to have to update everything that comes after it to make sure that that index is kept and that we don't have space within our array. So 2 things for us to actually think about. We're used to thinking of the capacity of an array, so how many elements can fit into it, which we use .length to access in Java. There's also the size of an array, which tells us how many elements are actually in it. And so depending on how many elements in our array and where we want to enter in our new value, we're going to have to move all subsequent elements to the right. So let's imagine we have 4 top scores, 10, 9, 8, 7, really simple. We now have someone who has 9.5. So they need to go after 10, but before 9. We're going to have to shift 9, 8, 7 to the right to be able to put that 9.5 where it belongs. And similarly, if we wanted to remove the 8, we would have to shift the 7 1 space to the left to keep that order. All right, so insertions and removals from an array are not as straightforward as we would assume if we want to keep the size of the array correct, as in however many elements are actually in that array are in the indexes or the indices 0 up to size -1. Then each time we enter something new into our array, if it doesn't go to the very end, if to keep our array sorted, it goes somewhere in between the existing elements, everything that now appears after it has to be shifted to the right. And similarly, if we remove something, so let's say we want to remove the 3rd high score, all the ones that appeared after that have to move up. So whoever was 4th will now become 3rd, whoever was 5th will now become 4th, and so on until we get to the size of our array, however many elements were in there to begin with. And so if we think about it, how long will that actually take? That means that our insertions and our removals are not constant time, right? Although lookups are constant time, as in we can get any element out of our array in constant time by using an index to index into a particular position. But if we're inserting or removing, that actually depends on how many elements are in our array. And in the worst case, an insertion or removal, if we're doing it at the beginning of our array, at the 0th index, can actually take up to the size of our array to do. Because after let's say we're removing, if we remove that element at the 0th index, everything that appeared after that has to be moved one position to the left. And so it'll take as long as time as we have elements within that array, and that isn't great. And certainly for our insertions, the same thing. If we want to insert something at the beginning of our array, then everything that was there has to be moved 1 space to the right. All right. We will get to algorithm analysis later, but you have done it before, so you should understand when I say that it's linear time. So if I have n elements, it'll take some multiple of n, depending on how much time each move takes. So each copy to a different cell will take some amount of time. Let's say it takes 5 milliseconds. So it'll be 5 milliseconds multiplied by n, the number of elements that were in that array. All right, so it's some linear time. All right, we use arrays a lot within our language, and so we have the arrays package within java.util that allows us to be able to do operations on arrays, like sorting, like determining if two arrays are equal. Remember that if we try to simply take two variables that point to arrays of the same type and try to check if they're equal, all that will be checked is, do they actually refer to the same memory address? So if they don't actually, if they aren't aliases of the exact same array, then that type of equality check will not say that they're equal, even if they contain the exact same values. What equals does is it checks element for element. Are there the same elements stored within these arrays? Of course, that means that these elements have to be comparable. But if they are and the arrays are the exact same length, then we'll return that they are indeed equal. Fill will simply take values and fill that particular array up to a certain point, fill from one array to another. If the one that you're copying to is longer than the other, then it simply puts in default values for the rest of the fills. Sort allows us to be able to sort an array, very useful. ToString then returns a ToString representation of our array, which is simply each element printed out with commas in between them and our square brackets at the left and right of it. Note, if you try to simply print an array using the variable that points to it, you would get what looks like a memory address, so a reference. It won't actually print the elements that are within that array. You'd have to use arrays.toString to do that. Then sorting arrays, you will have come across different sorting methods. So there are many different ways that we could sort an array. Insertion sort is simply an example, one example of how we could do that. You may or may not remember it. Let's remind ourselves. Insertion sort goes through an array left to right, keeping the left side of our array sorted, so that by the time we get to the end of that array, the entire array is sorted. So think, if we're at the 0th index, nothing occurs before it, so that single element at index 0 is sorted. Right? It's a trivial list, the trivial array of only one element, and so it's already sorted. If we go to index 1 and we compare that to index 0, if index 1, let's say we're wanting to sort in ascending values, then if index 1 is greater than index 0, then we're fine. The elements stored there in that fashion, then we're fine. However, if the element stored at index 1 is smaller than that stored at index 0, then we'll move it one to the left. We swap them. Then whatever's to the left is indeed sorted. Then we move to the next one, what's at index 2? And we try to find its correct position by comparing it with each one to its left until we find one that is larger than it, sorry, one that is smaller than it, because we're doing an ascending, and we then insert it after that one. And as we go across, each time we're looking at the current one and putting it at its correct position. We may have to go up to the beginning of our list, but we're going some number of values to the left to insert it at the correct position. And our entire list on the left of where we're looking is correct, is sorted. What's on the right may or may not be sorted. Then we keep going in that fashion, each time moving the current one as many times to the left as we have to get in the correct position. Once we get to the end of our list, it is sorted. As in, once we get to, there were n elements, we get to that nth element at index n-1, we compare it to the n-1 elements that occurred before it, we put it in its correct position, each time moving the one that we're comparing it to the right if it's larger than it. When we find one that's smaller than it, we insert it after that, everything will be sorted. All right, so that's one way that we could sort an array, and many different ones. We will discuss some as we go across, as we continue, because we'll find that there are some data structures that allow us to sort a list of elements in a more efficient way than when we have it in an array. Right. So there's a discussion of that in the text, but you should understand that, or if not, you will now understand. Oftentimes we use random numbers, or we need random numbers for our programs. If we think about the practical that you had last week, you guys didn't work on encrypting that data. However, that encryption was done by taking the letters of the alphabet in the normal order that they are, A to Z, and coming up with some random permutation of that. And so we'd have to use random numbers to just to decide where does each number go. So A would have gone to 1, right? If we'll think about an array to the 0th index, but we're going to find some random number between 0 and 25 and assign it to there. So you could use a random number generator to come up with random values to decide where you should put or where you should map your particular characters, and that would come up with a way to encrypt a message, some private message that you don't want to send out in plain text, and create some cipher text based on that. The example that's given in the text is that of a Caesar cipher, which is a slightly simpler version to what we considered. This one simply shifts the characters some number across to the right. So for example, if we're doing it by 2, then A will be mapped onto C, B will be mapped onto D, and so on. So it decides on some number to shift all the letters across. This is done in circular fashion, so Z would then go to B. All right. Another example would be positional games. So just think if you've played a game where there are characters and NPC, non-player characters, those non-player characters are usually spawned at random positions within our game. So if our game is thought of as a flat 2D area, then by coming up with two random numbers, I and J, that represent positions on the screen, the program is able to randomly spawn these non-player characters in a different position each time. And that keeps it interesting. If they were to spawn in the same place each time, you could predict that and simply go and do what you must with them that way. Granted, a machine can't actually come up with a random number because you have to give it an algorithm for it to decide what number to choose next. And so instead it comes up with pseudo-random numbers, which we already discussed. Pseudo means looks like, but isn't necessarily. So a pseudo-random number isn't actually random. Instead, it uses a seed, so some initial value to use within an algorithm to generate the next number. Which means that if you use the same seed each time, you will end up with the same sequence of pseudo-random numbers, which is not what we want. And so you can use a truly random seed to be able to create random numbers. Oftentimes we'll use something like the time right now on your computer, which is the time from some value, from some initial value, I believe it was 1970. And so that allows you to be able to come up with a seed that will not likely be used again, right? The time will never be up to the millisecond what it is right now. And so you're able to give that as a seed and come up with a random seeming sequence of numbers should you need them. So oftentimes we use 2D arrays for different types of games. As I said, if we're trying to spawn characters on a positional game, we'll use a 2D array that we think of as a matrix. You can also think of tic-tac-toe as a 2D game that simply has a 3x3 matrix, and you could randomly place an X or a 0 there, and you can also write a method that will be able to calculate, well, has anybody actually won this game? If I go across diagonally or horizontally and vertically and check, do we have the same type of mark at each of those positions, we can actually determine whether someone has won a game of tic-tac-toe. All right, a couple of questions, let's answer those now. Are the future packs also including ciphering and deciphering? As I said, we will put in an element of that because your mini project has to do with such things, right? So I will introduce that as much as possible while sticking to the data structures that we're discussing each week. All right, doesn't mean that every single prac will include that, but some of the pracs will include that. So you get used to the ideas that have to do with what your mini project is concerned with. Why do we consider multiple sorting algorithms and not just the most efficient one? Will there be a case where one is better suited than the others for that specific task? All right, interesting question. Certainly, to appreciate the more efficient ones, we talk about the ones that are less so. And oftentimes we'll see that although in ideal cases, we can have two methods that seem to have the same efficiency, there's some that on average perform better than others. And when we get to our section on computational analysis, we'll look at exactly that. So one reason we look at them is to compare them. Another as well, we want to kind of talk about the evolution of these methods. And also, some are simpler, as in simpler to express than others, or they simply use less space than others. So if we want to use a divide and conquer strategy, we understand that each time that we recursively call a method on smaller and smaller problems, so let's say we have this array, we want to sort it, we want to use quicksort, so we'll choose a pivot element and split our array in two, and each time recursively call that method, you understand that's actually using more and more space in your machine. At each time the recursive calls makes that method, a new instance of that method is created with the values that are passed to it as an argument, and so you're using more and more space. Certainly if we're sorting an array and we need another array to be able to do that sorting, so we can't do an in-place sort, then we're using more space than if we're doing an in-place sort like the insertion sort that we looked at. So there's some that may be more computationally efficient, however, they use more space. And so space is an issue and not computing power, then would rather use those. So there are sometimes different instances where one is more efficient in a way that we are concerned about, even if it isn't computationally efficient. All right. But that's a good question. And certainly when you get to honors and you actually look at implementing full programs, specifically I teach parallel programming, and when you're going to use a parallel method, you have to compare it to the most efficient serial method, or else you're kind of pretending that it's more efficient than it is. That's really important. All right, so basic ADTs. We talked about the fact that if you distill a data structure to its most fundamental parts, which is what data does it store and what methods does it have to manipulate that data. So if you apply the idea of abstraction to a data type, then you end up with this idea of an abstract data type. A data type that is simply a description of what it stores and what methods it has to manipulate that data. And in fact, if we're using our generics framework correctly, we can define this data structure in such a way that it can work with any type of data. And so we're concerned with what operations can we do on that data. Granted, that may be a bounded type of data because we are able to bound our types using the generics framework. So the idea is that we're going to describe them in such a way that the implementation is abstracted away. It does not matter what specific implementation we're using, but rather as long as the operations are as we have described them, and in Java, we'll use an interface to describe that. Right? Because isn't that exactly what an interface does? It's a description of the methods that will be present within any implementation of that interface without any description of that concrete implementation. Simply, these are the methods, these are the parameters it accepts, this is what it spits out, but no discussion of that implementation. And so we'll find that there are many different ways to implement any of the basic ADTs that we're going to discuss. All right, and the first such one is the position ADT. So the idea of a position is that it models the notion of place within a data structure where single objects are stored. So we have some data structure. The only thing that we really define is that each of the elements that are stored within this data structure have some position. They have some place within the order of this data structure. It gives us this unified way of storing data, of thinking of the way that data is stored. This could be in the cells of an array or in the nodes of a linked list, but it works for all of them because each element in our array is at a particular place within that array. Each node within a linked list is at a particular place within that linked list. Granted, those have a linear ordering, right? I move in a single direction or in two directions, but along the same, how can I put that? Along the same axis, and so in a singular way, in a linear way. and we'll get to more complex ones. But a position ADT just allows us to abstract away that idea and simply say that we can store an element within some place within a data structure. And so this position ADT has a single method called element, which just returns the element stored at that position. So you can think of a position as this type of thing that encapsulates our element. It stores it within this larger data structure, and we can call its method to return that element that is stored at that position. All right, and that's our first abstract data type. And yes, to create a concrete position, we could use the cell of an array. We could use the node of a linked list. Then what is a list ADT? Well, if we think of a collection of elements, right, there's nothing defined on that collection besides the restriction that they should be similar. If we think of an analogy, if you're looking at a mathematical set, then the only restriction is that that collection of elements, that collection of things, must be of the same type. So if we have now in Java a collection of things, they must be of the same type. If we now define some ordering on them, then we can create what we call a list ADT. So this models a sequence of position that stores arbitrary objects. So now we have these positions, each of which store an element. Now we're going to add the idea of a sequence, so some ordering on them, and that allows us to create a list. So now we have a list. It can store positions, and it has some order on them. Well, if there's an order on them, that means that I can find what is the very first thing in that order, what is the very last thing in that order, and if I'm at a particular position in my list, I can ask, well, what occurs just before that position, and what occurs right after that position. So if you look at our accessor methods, they're exactly that. We have a first method that returns the very first position within our list, a last method that returns the very last position of our list, and then a previous P, which given a position will return the position just before that, and next P, which given a position P, will return the position just after that. We have previous and next as well. We have generic methods, which we have in many of our different data structures, whether linear ones or not. Size is empty. Size returns the number of elements that are stored, or rather the number of positions that are stored within our list ADT. So not the capacity of it, but rather the size. How many things are actually currently stored within that list right now? And is empty, well, if there are no elements stored in there, is empty should return true. If there is something stored within our list, is empty should return false. We also have update methods, replace, which takes two arguments P and E. So at position P, replace whatever is contained within that with E, and will usually return what was stored there before. Insert before also takes two arguments, P and E. So you're saying insert in a new position before the position P containing an element E. Insert after, given a position P, create a new position after that, and store E within that. Insert first stores the given E at the first position within our list, and insert last inserts, and both these actually create new positions to store this. Inserts creates a new position and stores it at the end of our list. Remove P removes the given position from our list. All right, so cut that out of our list. All right, you'll note that the old text uses insert before and insert after. The new text, the current one, actually uses insert between, where given two positions, create a new position in between them and store an element within that. We'll see from our implementations that this is actually equivalent. If I have an insert before method, then I can actually implement, or rather call that method to implement insert after. It's much the same for insert between. All right, but we'll discuss that as we come across it. So a singly linked list could be one implementation of a list. It does indeed allow us to store arbitrary objects, and it allows us to define some order on them. There is some first element within the singly linked list, or specifically a first node that stores an element, And we can tell what comes before it and what comes after it, our previous and next, and there is some last one there as well. And we're able to actually add things before and after a given node in our linked list, so it does satisfy the methods of our list ADT. So how do we actually construct this list ADT? So, or rather, single linked list, which is an implementation of our list ADT. So a single linked list is a concrete data structure. So not just a description of what a list should contain, it's a concrete data structure that consists of a sequence of nodes. Each of these nodes store an element, so they do satisfy, and in fact, if we have a method that can retrieve that element, then it can be an implementation of our position ADT. However, each one of them stores an element and a link to the next node. I have a little diagram that describes that. So each one of them stores an element. If that's a reference type, then the element would store a reference to whatever element is stored there, and a next link that simply links it to the next node in our sequence, in our single linked list. So this is what a single linked list with multiple nodes would look like. We have some initial one. Note there's no link pointing to that particular node. It points to the next node, the next node, the next node. The last one points to nothing, so we store null there. Each of them contains an element A to D. So if you look at a concrete implementation of our node class, it would look like this. It stores an element and a link to the node next to it. If we're using our generics framework, we wouldn't create element of type object. Instead, we'd pass a formal parameter, let's say E, and our element would then be of type E. So we could do that instead. Our default constructor simply creates two null references. So the element stores a null and our next thing stores a null as well. If we instead pass some object and reference to a node, then we store each of these in our element and next respectively. It has an accessor method, get element. Okay, all we do then is return our element. For our get next, we simply return that link to the next node within our list. Set element, we then set elements to whatever element is given to us, so that replaces the previous one. And set next, we can set our next link to some other node. So we can change which link, we can change our link to point to a different node. So how do we go about inserting at the beginning of our list? Or we call inserting at the head. Well, you'll note that we'll have to have some reference to the beginning of our list. If we don't have a reference to our list at all, then Java's garbage collector will simply destroy that because no one can actually work with that. No one can refer to that list. So we'll use a reference that we call head that points to the beginning of our list, the first node within our single linked list. All right, we can also use a second reference called tail that will point to the very last node within our list. We'll find that will make inserting at the end of our list a lot easier. But for now, we're just concerned with inserting at the beginning of our list. So to be able to do this, we want to insert a new element into the beginning of our list. We will create a node to store that particular element, insert that new element into that node, then have that new node point to what was the head of our list, then update head to be that new node. All right, so head will now point at that new node. That effectively creates a new head node, so a new node at the beginning of our list. Note steps 3 and 4 have to definitely be done in that order. If instead we updated head first, head would now point to our new node. We'll have lost the entire list that we had in there before. So we have to first use head to have our new node point to what was the beginning of our list before, so what head was pointing to, then update head to point to our new first node of our list. Okay, we have a question that regards this. In the case of a linked list, which is the reference? The head of the node or the element itself? Well, they're both. Well, if it's not intrinsic data types that are stored as elements, then both of them would have to actually be a reference type. Though granted, head is not actually an instance of a node object. Head is simply a variable that can refer to a node object. And so we use that to refer to the first element in our list. Element, well, if we're storing an actual element within each node, then we'll store the reference in element, but it should point to some instance of whatever type we're storing within our list. So let's say we're storing the same kind of type we were working with last week. So one that stores a character and some integer that represents rank, could also be a double. So each one of these elements would then store an object of that type. Well, we store class types, objects, by storing references to them. So element could either be a concrete type. In fact, by using generics, we don't have to worry about that. Although because we only accept class types, we'll have to use a wrapper type, but that simply stores a single instance of an intrinsic type. So it'll store some reference to a concrete object, an actual instance of that object. If it stores none, that means there is no element there, and there'd already be no point in including that within our list. Each of our nodes has to store an element within it. All right. Yes, it can store none. That doesn't really make sense unless we're working within a situation where we give null some meaning. All right. So that's how we'll store something to the beginning of our list. How do we store something at the end of our list? Well, if we don't have a reference to the very last node in our list, then this becomes not difficult per se, but it will take more time. If we didn't have this tail reference that refers to the very last node in our list, it would have to begin at the beginning of our list. So access the node that head points to, and then link hop. So go from one element to the next, to the next, to the next, to the next, using those next links until we get to the very last one, and then we know we're at our tail. So it's a lot simpler for us if we want to be able to do this in constant time. So regardless of how many elements, it'll take the same amount of time. Then a stored in our list, then we would have to have this tail pointer. So let's say we have this reference to the very last node in our list. Then to add a node to the end of our list, we simply again create a new node, store that element within that new node, make that new node's next point to null, because that actually tells us it's the end of our list. If it points to nothing, it must be the end of our list. Then using our tail reference, we update the next link of our formerly last element to this new element, then update tail to point to the new element. Again, 4 and 5 have to happen in that order. If we simply update tail first, then we'll have to go back to the beginning of our list and link hop until we get to the last element, and then update its next to point to the new last element. If head is our only node, then it's both the head and the tail, exactly that. All right, it'll be the head because head points to it, and whether or not we have tail, its next will point to null, so it is the last node of the null list. And we can have that. If we have a list of a single node, and a single element stored within that node, then it is both the head and the tail of our singly linked list. What about removing at the head? Well, it's actually very similar to inserting, but in fact a lot easier because we don't have to do the 2 steps of creating the node and installing the element there. Instead, we just update head to point to what head.next was previously pointing to. So whatever the first node is pointing to, which will be the second node, we update head to point to that. Note if that was null, so if there was a single element in our list, then it will be updated to null, which would make our list empty, which is still correct. So we update head to point to whatever the first node is pointing to. And then because there's nothing referring to the node that was our first node, Java's garbage collector will simply reclaim that, destroy whatever was there. All right. Granted, we will usually return whatever value was stored at there each time that we remove something from our list, and would have to decrement, so we'd have to reduce the value of our size by 1. And when we were adding things to our linked list, we should, to keep our size correct, increment that, add 1 to the value of our size. And then what about removing from the end of our list? Well, again, we'll have to update tail to now point to the node before the tail. However, because we only keep references to the next node within our list, we can't access a previous node, a node that occurs before the current node that we're looking at. There's no way for us to do that within a single linked list. So there is no efficient way of doing this. There is no constant time way of doing this, as in it will actually depend on the length of our list, how long this takes. We'll have to begin at the beginning of our list by accessing head, then link hop, as in go to heads next, then the next of that, then the next of that, then the next of that, each time checking, is the next equal to tail? So is it that same node that tail is referring to? When we get to that, when we find that the current node's next is tail, then we'll change that current node's next to null. Because then that breaks the link between the second last node and the last node. Then when we update tail, nothing is pointed to that last node, and it's then taken by a garbage collector. We've effectively removed it from our list. However, note, because we don't keep references, we don't keep that link to the node that occurs before any node, so to a previous node, we can't do this efficiently. We will have to go through the entire list to do this. And so the time that takes depends on the length of our list, which is not very efficient. If we have 1 million elements in our list, our single linked list, we will actually have to link hop 1 million minus 1 times and then remove that last one. You will have discussed stacks. We will discuss the stack ADT, so the abstract data type based on a stack. But for a concrete stack, you will remember that a stack, like a list, has a linear ordering. However, we're only able to access and add elements to the top of our list. Right? So perhaps I should just draw a little picture so we remember this. Okay, there we go. So we can think of a stack. All right, the nudge is usually used as that of a spring-loaded plate dispenser. So you have some spring here, you have a plate over there. So it's a type that you find at a buffet. And we're able to add elements on top. We're able to access, so to look at elements on top, we usually call that peek. And we're able to remove an element from there, and we'll call that pop. And we're able to, okay, this peek simply looks at what's on top there. But we're able to add things on top as well, and we'll call that push. So it has a method to add and remove from the top, and it has a method to look at, so to access whatever element is stored in that node or whatever type of object we're using to store that element. However, there is no way to access the things that are under that. You can only access things at the top. All right, so hopefully that reminds you of what a stack is. So could we implement a stack using a single linked list? Yes, we could, because the single linked list is actually more powerful than a stack, as in we can access things at the front, at the end of our list, and by link hopping, we can access things anywhere within our list, right? For a stack, then, we'd have to choose what's going to represent the top of our list. So we'd be able to add and remove from there and access things there. And everything else would then be inaccessible. So we could either choose to have the head as the top of our list or the tail as the top of our list. Which would we choose, the head or the tail? Head, tail, head. All right, so can we add and remove things from the head? Yes, we just discussed that. Can we add and remove things from the tail? Yes, we just discussed that as well. However, we saw that adding things at the head, so we'd call add first, was constant time. Okay, we'd say that it takes order 1 time. Okay, we'll get to all this if you don't remember it. But it does not depend on the size of our list. We simply create a new node, store the element in that, have it point to head, update head. Then remove first. So to remove from the front or the beginning of our list would also take order 1 time. We simply update head, we're done. Then adding to the end of our list, so adding last was also constant time, right? We create a new node, store that new element within it, update tails next. So whatever node tail is pointing to, we update that next to point at the new node, and then update tail. The number of steps does not depend on the size of our list. However, the remove last we found depended on the size, so n, how many elements are within our list. So whilst we can add and remove from the front and the back, we would rather choose the front of our list to represent the top of our stack because we can add and remove in constant time. All right, so by understanding these, how long these methods take, or the complexity of them, we're able to choose the correct one. So we'll take the top element as the one stored at the front of our list, so the first node. Then the space uses order n. Well, that makes sense. Regardless of the size of each node, it'll be n multiplied by that size will be how much space we use. Granted, each of those nodes is storing an element and a reference to the next node, but it'll be order n because it'll depend on how many of those we have. Each operation will take order one time, so it'll be constant time. It will not depend on the number of elements we have within our actual list, although now we're using a list to represent a stack, so it won't depend on how many elements we have within that stack. All right, so do we see how we can actually use what we call the adapter pattern, where we already have an implementation, we want to use that to define a new data structure. We can create an instance of the singular linked list, which we should have implemented, and simply call methods within that list to implement our new data structure. All right, we wouldn't want people to be able to access any arbitrary elements or any arbitrary nodes in our singular linked list. So we'd make sure that our instance of the singular linked list is private and only expose the methods that should exist within a stack. So we'd call it push, and push would simply call add first. Pop would call remove first, and peek would call first. Right? It would simply return head that reference to the first element. Then what about a queue? Do you remember what a queue is? So again, a queue represents something we have in the real world. That's a horrible stick figure. But oftentimes we will have people. These can be people, these can be processes waiting to get access to some resources. But we have a queue and would like to service these requests, right? Even if the server is a cashier, right? And you're starting to queue at a grocery store, we would usually service those requests in what's called FIFO fashion. So first in, first out. So when people come to join the queue, where would you add those people? Would you add them at the front, in the middle, or at the end? What would be fair? Just think, when you're standing in a queue and someone comes to join that queue, should they be added in front of you, in the middle, perhaps in front of some other people, or at the end? Yes, they should be added at the end. So a new one gets added there. And then how about who should be served first? Should it be you who's at the front, or someone behind you, or someone behind that, or the person who arrived last? Front, right? It should be the first person. So first in, first out says that the one who arrived first will be served first. Certainly you. Whereas additions will be done at the back. So again, now we have options. We could make the front of our queue equal to our head, so the first element within our list, or we could make the back of our queue the head, the front of our list, and then have the front of the queue be the last, or the front of the queue the end. However, remember, because we are removing from the front and adding to the back, we'd want removals to be constant time and those insertions to be constant time. So because, as we just discussed, removals from the front within a single linked list are constant time, however, removals at the tail end are not constant time, we would choose the front of our linked list as the front of our queue, would use the tail of our linked list as the rear of our queue. All right, that's useful because then add or insert into our queue becomes constant time, and remove from the queue again becomes constant time. Because we can remove here, remove last, remove last in constant time, and add first. Oh no, I'm doing that the other way around. Sorry, that should be add last and remove first. We can do those in constant time. So we can use a single linked list to create a queue by using these two methods. Remove first to represent adding into our list. Add last to represent adding to our list, and remove first to represent removing from our queue, which will always be from the front of that queue. All right. So again, we learned something really powerful. If I've created a single linked list, I've actually implemented it, then I can use that implementation to define a new data structure, a queue. Question, can't we remove from the tail in a queue? No, because that would be unfair. Unless, of course, this is a different type of ordering to look at. Perhaps you look at LIFO, so last in, first out, but that would be, for a different use. Yes, you could do that, but then you have to update your add and remove methods within your queue to make sure that you're then perhaps adding from the rear and removing from the rear, but then it'll be more convenient for you to use the front of your linked list as the rear. So if you're simply adding and removing from the rear, then you'd use the front of your linked list to represent the rear because both those operations would be constant time. But if we're using a regular queue that follows the rule of first in, first out, then yes, we could insert at one end and remove from the other end. Which ends those are doesn't matter. But because we want it to be efficient, we would insert at the rear, which is constant time, so at the end, at the tail of our linked list, and remove from the front of our linked list because that's constant time as well. So the front of our linked list, that head would represent then the front of our queue, and the tail of our linked list would represent the rear of our queue. So you could do either or, but this is the most efficient way of doing it. Then our queue operations, which is simply add and remove, become constant time because one of them calls add last, the other calls remove first, which are both constant time, and the space uses again order in. We don't use any additional things. We simply have these references front and rear, which we had as head and tail, and we have some multiple of whatever size our nodes are. So n times whatever size our nodes are, and that's order n. All right, so how would we actually implement this in Java? All right, someone has their hand up. You can go ahead and turn your mic and ask your question. If you don't have a mic, then you can type it in as well. Okay, so whilst that person is, I guess, typing in their question, you have another question here. Adding to the previous question, can't you remove the tail, then update the previous element to have it point to null and have that be the tail? Yes, that would be how we. Oh, okay. Oh, you're talking about removing from the tail. All right, so then let's go and take a look at that. So you're saying, can't we remove this, right? And then update the previous element to have it point to null. That's a terrible null. Okay, update it to point to null. How will we get to this reference? How will we get to this? Okay, how do we get to that from the previous one that we had? So I was here, so I'm here. How do I get there? Okay, yes, there's no link to the previous element because it's a single linked list. So we cannot get from here to there without going to the beginning of our list and then link copy. Saying head and then update. Let's say we say, okay, our start is equal to head. So that copies the reference that was stored in head, right? And puts it in start. And we say start is equal to start.next. So that moves us to the next one. Then the next one, then the next one. Each time we check, is start.next equal to our tail? When it is equal to our tail, then we know we're here. Then we can update this reference by saying, okay, our current nodes.next is now equal to null. However, we'll have wasted n operations doing that. Make sense? Grant is actually n minus 1, though we do actually do that first one to head, so anyway. But that's n minus 1 is still order n as well, still linear time. So do we understand why we wouldn't want to do that here? Because there's no way to access this one. Whereas if we start at the head, all we have to do is update head. That's it. And everything else falls away. Granted, we would first put whatever head is pointing to in some temporary element. So sorry, in some temporary reference. Then head is equal to head dot next. So these two lines allow us to store whatever head was referring to, then make head refer to the next node in our list, and would then return temp. Those three lines allow us to remove from the front. Nice and simple. Removing from the tail there, a lot more complicated. So we wouldn't want to do that. Then someone asks, so are queues and stacks type of linked list in which we can think of this hierarchy? Now, a queue and a stack are completely different data structures. However, what we're showing here is that we can use a single linked list to represent a queue or a stack. So if we think of this, we want to use a queue. Oh, someone says they can't see the cursor, by the way. Can none of you see the cursor? If I'm drawing here, can you see that? Nope. Okay, some can and some can't. All right, and that's an even more. Oh, okay, you can't see the. Yes, you won't see the cursor. All right, so you say when I'm pressing down, it does show a little red dot there. Okay, we don't have to worry about the cursor. When I want to refer to something specific, I'll either refer to it by its name, like, head or tail, or I'll draw something there to indicate. All right, so you don't have to worry about the cursor. Simply what's drawn there is what matters. Okay, as long as you can see the annotations itself, that's what's important. All right, so just before that, I want to answer the questions before we discuss whether or not that can be seen. Someone asked, okay, so are queues and stacks type of linked list? No, those are different data structures entirely. So we have the list that we talked about that's simply the idea of storing positions within some order, right? And we have to fulfill certain, let me go back actually. This is the list ADT. It's a description of methods. This is the behavior of a list. How can we implement a list? In many different ways. We look at one way, which is by using the concrete data structure, single linked list, to implement all these methods. First would simply return head. Last would simply return tail. Previous P, well, that would be quite difficult within a single linked list, but we can do it. We simply begin at the head and link hop until the next is equal to P, and then return that current one when next is equal to P. Next P, very simple. We simply return P.next. Replace PE, or we're given P and want to put E there. You simply then say P.set element E. Insert before, again, would have to link hop. Insert after, where you simply create a new node, store that E within it, and add it to the list there. And that's simple enough. We'll look at that. Insert first, well, we looked at how we could insert a new element at the beginning of a single linked list. So we'd call that method to insert first to actually do this list method of insert first. We would call insert last So inserting at the tail to implement insert last. And remove P, that one's also a little difficult if we're not removing from the beginning or the end. So we looked at how we can remove from the beginning at the end. We'll discuss how we can remove anywhere within our linked list to satisfy the method remove P that is, that is described within our list ADT. Right. So when we say implement, we understand that we can express an abstract data type through an interface. Then to implement that, we would actually create a concrete class that implements list, which means it has to have all these behaviors. And what we've seen is that we can actually implement a lot of these using the methods that already exist within a single linked list or define new ones. And that's what we want to look at. Can a single linked list satisfy the requirements of a list ADT? So can we use a single linked list to implement the list ADT? Then we saw that actually we can use a single linked list to implement other data structures, and quite easily. We saw that we can use a single linked list. There we go. To implement a stack or a queue very simply. They call methods that already exist within the single linked list, and they're all constant time. So we can actually quite efficiently implement a stack or a queue with a concrete single linked list. All right, but those are different things from a link because, sorry, from a list, they're actually less powerful. They don't allow arbitrary accesses, inserts, and removals. They only allow you, let's say for the stack, to access, insert, and remove from the top, and from the queue, for the queue, you can only add to the front, remove from the back. All right, then there's some other questions. Maybe we take a 5-minute break. I've been holding it for an hour. Sure, go ahead. I'll just be answering questions now, and this is recorded. From the prac, for the prac, we'll make use of JavaFX. I've already answered that. Some of the pracs will require you to create a graphical user interface. How efficient are arrays in the implementation of a stack or queue compared to a linked list? Good question. I'll answer that now. Can stacks and queues be implemented without using a linked list? Yes, certainly. We can use other things to represent that. And that question was asked before. Can an array be used to represent a stack or a queue? Let's think of it. We have an array. We said that if I have, let's say E1 is stored there, E2, okay, they don't have to have names because an array will use indices to actually allow you to access elements within an array. Can I easily add things to the beginning of my array? And can I easily remove things from the beginning of my array? Not so. We just learned that if I remove this first one, I have to move this one up and move that one up as well. Right? Because my size is now 2, which means I would expect that index 0 and 1 are used. So I have to remove those things, remove that one that I want to remove from the beginning of my array, and then shift the others to the left. If I wanted to add something, if I now want to add some E3 there, sorry, some E4, some other element, I'd have to shift E2 and E3 back to the right. So it's not a really easy way to do this. If, however, I want to add, let me remove this. If instead I decide to add and remove from the end of my array, then what we find is it actually becomes really simple. If I want to add a new thing, I simply go to the index size. So size is 3 right now, I go to 3, and I change, let's say my array was named A size, to whatever my new node that I'm storing there is. All right, so whatever object represents my position and I'm storing my element within, but for ease, I'll just say E4, and that goes in there. If I want to remove from the end of my array, what do? I store in temp array size -1. Okay, because actually this should have had a plus plus of size after that operation. So I go to array size -1. That's where my last one is stored. I then can return temp. And how do I remove this from the array? Well, actually, if I just say size, decrement size, I then think of the size as just being this. And so it doesn't matter what's there. When I add something, it'll overwrite that. So that's a very simple way to remove. So this would be how I add things to my array. This would be how I remove things from the end of my array. So we could very easily use an array to represent a stack. However, with a queue, we want to add at one end and remove from the other end. So that would be a little more complex. That either our insertion or our removal could be constant time because they're at the end. However, the other operation, whether it be, so let's say we want to insert at the end, then our removals at the front of our array would be difficult. They would take order n time because I have to shift everything else to the left. Or the opposite, if we are inserting at the end, then that's very simple. However, removing, sorry, no, if I'm inserting at the beginning, that would take order n time. Our removals from the end would then be constant time. So, interesting question. Yes, an array can be used to implement a stack or a queue. However, we see that for the queue, it's not as efficient. Next question, C++, we could implement queues and stacks using dynamic arrays. Is there a way to implement them with arrays in Java? Actually, there is. I've just taught you there how you can do it for a stack. And for the queue, we've just gone to the point where you see that it's not that great. However, there is a way that still using that same array, we can efficiently represent a queue. And this would be this. E1, E2, E3. Then let's say we want to do an insertion. We do insertions from the end of at the end of our array. So we learned that's very simple. We just insert it there. Then we do removals from the beginning of our array. However, instead of assuming that our array begins at index 0, we will keep a reference to the front of our queue, which initially is 0. However, when we remove from the front, we increment front, and the new front becomes this. By doing that, we now only consider the array from here. Granted, we have to work out our indices by calculating size minus front, or the size plus front to work out the correct index. But it allows us to be able to remove and add in constant time. So now we can insert into our queue and remove from our queue in constant time. But to make sure that we're not wasting our array, we'll do this in a circular fashion. So when the next index is the length of our array, then you should go back to the beginning. Granted, the array is still a fixed size, as all arrays are in Java. And so when your rear reaches the front, then you know that your array is full. All right. And then someone was talking about some other things here. Let's see. Dynamic arrays. I've already told you that dynamic arrays aren't actually dynamic arrays. They do use fixed size arrays within them. It's simply that when you get too close to when the array gets full, it creates a new array, destroys the old one, or creates a new array, copies everything to the new array, and then updates the array to the new one, thereby destroying the old one. Is an array a position ADT? Well, if we're using an array, then the elements of our array, right, the actual cells, let me say rather, of our array would then be the positions. Right? They would store a single element. And a method that we could use to return those is simply the array name and the index. All right. So what are the similarities between an array list and a linked list? We're not going to even use the term array list because when we say array list, you all assume the actual concrete data structure that's defined within Java, which you use to create dynamic arrays. However, An array list as an ADT refers to what's called an indexed list. A list that has order, right? It is a list, but it also defines an index, which is a number that represents the number of elements that occur before a particular element. We will get to that in later chapters, but just note that we don't use array lists because they mean something else rather than the concrete data structures you're thinking of that are implemented in Java that used to be called vectors, or a different version of which were called vectors. Array list in Java is a stack, right? Can you not do arbitrary inserts and accesses within an array list? Can you access any element in an array list? All right, while you think of that, yes, well, then it's not a stack. A stack only allows you to access what's at the top of the stack. Is there some hybrid data structure to easily store, perform, add, and remove without the complexity of both arrays and linked list? We only choose the good properties like indexing and easily adding elements with linked lists. Okay, because linked lists don't actually keep an index, they allow us to easily add and remove at arbitrary positions. However, with a single linked list, we saw that we can, while it's pretty simple to add something after a particular node, it's difficult to add before it because we don't keep references to the one before. So we'll see that a doubly linked list is an even better implementation of a list because we can do arbitrary inserts and removals even more simply. When you find that removing at the, removals at the tail then become constant time as well. Are linked lists zero index like arrays? No, linked lists don't actually have an index defined on them. If you want to use an index to access the elements of a linked list, you would have to start at the beginning, increment whatever variable you're using to 0, and then link hop until you get to whatever index you're looking for. So it does not store indices. You would have to very difficult link hop, or rather wasting a lot of time link hop to get to the next. All right. So the implementation is given within the text. You can go look at those code fragments there that actually show how the implementation is done. Insertion, we saw how we can do this at the head and the tail, but what about adding in the middle of our linked list? So how could we add to the middle of our linked list? We can actually do this. Let's say we had a linked list. If we wanted to add something here, then again, we would create a node, store in that node whatever element we want to store at it, update its next to point at, let's say we're adding after this was P, then we'll update this to be P.next, and would change P.next to refer to this new node. That changed this, and that element has effectively been added to our list in constant time. As long as we had a reference to this P, we could easily add after P. Adding before P would be more difficult because we'd have to have some way of accessing this. And so we would actually have to link hop until we get to the one before P and then update that. Right. What about removals? We saw how to remove from the front of our list. That was fine. We said that removing from the tail end of our list would take link hopping. Removing from the middle, well, we can remove something that occurs after a node quite simply. Let's say we wanted to remove whatever occurred after P, then that would be simple enough. But if we want to actually implement our list operation of remove P, we would have to go through our list from the beginning, right, from the head, each time checking, is the current node's next equal to P? When the current node's next is equal to P, then we'll update the current node's next to be equal to P.next. That effectively does that. and that excludes P from our list. So note, removal from the head is simple, it's constant time, but removing from the tail end and from the middle depend on the size of our list, because we'd have to do up to n minus 1 link hops. Then what does P and E represent? All right, P represents some position within my list. E represents an element stored at a position within our list. We just lose this reference when removing? Yes, because then Java goes ahead and gets rid of anything that does not have something referring to it, because now it's orphaned. Nothing is referring to it, which means that you cannot use it within your program, and so it'll clean that up. All right, so what we see is that we can implement a list using a singly linked list. The space used to store n elements is order n, depends on the number of elements that we're storing. The space used by each position of the list is order 1, so it's constant, doesn't actually depend on the number of elements that there are. Most of the operations in list ADT now run in order 1 time, except for some access methods, and the operation element, which simply returns the element that's stored in the position, also runs in order 1 time, because all it does is you return the element stored within a node. So that's constant time. All right, I'm going to go back real quick just so we see those methods so that we're happy with them, or we understand what we mean when we say that most of them are constant time. First, yes, that's constant time. We simply return head. Last, we return tail. That's constant time. Previous, no, that's not constant time. Because we don't have any reference to previous, we have to link hop from the beginning. Next, that's constant time. Replace PE, yes, that's constant time. If I have a reference to P, I can simply replace the element stored at it. Insert before, not constant time. I'd have to link hop. Insert after, yes, constant time. Insert first, yes, constant time. Insert last, yes, constant time. Insert P, no, sorry, remove P, that isn't constant time. I'd have to have a link, I'd have to have a reference to the node that appears before this current one to be able to update its next to exclude P from my list, which means that for previous P, insert before P and remove P, I do need a reference to the node that occurs before it, and so those will depend on the size of my list because I have to link hop. Those are not constant time. Are we happy with that? Okay, if you're not, please ask now so we understand. I can implement a list using a singly linked list. However, some of them work very nicely, some of them don't. So whenever you need to traverse the list, it's not constant time, yes, because it can take up to n hops. If I'm looking for P some position within my list, I don't know where it occurs in my list, I'll have to search through the entire list, up to the entire list, to get to it. And then when I'm looking at it as the next thing, I can update that one's next to exclude it, or to add something before it, quite simply. All right, great. So if we understand why all of those are as described there, so then why is insert after constant time? Well, let's see. Let me quickly draw a single linked list. Okay, let's say this is P. I want to insert after P. I create a new node. I store whatever E I want to insert there. I update P's next to point to the new element, so the new node. I update, oh, actually, I shouldn't have done that first. I should have updated the new nodes next to point to p.next. That works correctly. Then I update p's next to point to this new node, and that's it. It's inserted. It takes that many operations. All right, 1, 2, 3, 4. Create node, store element, update new nodes next, update p's next. 4 primitive operations, and it takes that many operations regardless of the size of my list, And so that is constant time. It'll always be 4. All right. Then what about doubly linked lists? Question. So for next P, aren't we hopping through the list to get to P, in which case may not be constant? No, just think of the method there. Next P. You have to give me P for me to return next P2. And all I'll do then is for next P, I'll say return, it's terrible, P next. Granted, next may be private, so I'd simply call P's get next. That's fine. You should understand what I mean by that. So there's the implementation for return P. It is constant time. It's a single operation. All right. Great. Then what about a doubly linked list? How does this differ from a singly linked list? Well, for a doubly linked list, we again have a node. Each node again stores an element. However, now instead of storing a single reference link to the next node, we store a reference to the next node and the previous node. We also, usually by convention, use 2 sentinel nodes, one called header and the other called trailer, which store no element, but have 2 links, one to previous and one to next. Heads previous will be null, trailers next will be null. We find that by having these sentinel nodes, it allows us to simplify our operations, because now inserting at the header, or sorry, inserting at the head, not the header, so inserting at the beginning of my list, so one insert there, or inserting at the tail of my list, so before my trailer, will be the same as doing an insert in the middle of my list, because I will always have something before any node and something after any node. Even head will have the header before it. Even tail will have the trailer after it. So if I can define an add between method, then add first just becomes add between head and head.previous. Adding at the end of my list, so adding at the tail, then simply becomes add between trailer.previous and trailer. All right, so it's very useful. What's the difference between linked list and the blockchain? All right, you can go look up blockchain. There's a succinct enough discussion on Wikipedia. Prof. van der Hart will also give you some videos. Yes, blockchain does use what are called Merkle trees, where, okay, it's not a list firstly, it's a tree, which we haven't gotten to yet, but we'll get to, where each leaf, so each node at the bottom layer of that tree, stores the hash of some data, and then all the nodes that are the parents of those store the concatenated hashes of its children nodes. So it's not a list, it's not a single dimensional thing. It looks more like a tree. It is a type of tree. But the point is this, because this stores the hash of some data, and this stores, let me call this hash 3. This will be hash 1. Hash 2. Hash 1 is the hash of D1, hash 2 is the hash of D2, hash 3 is the hash of the concatenation of H1 and H2. So if at any point you change something, if you change this, then this hash changes and this top hash also changes. And so I can actually kind of tell where a change has occurred. All right. The idea is you're trying to make a chain in such a way that no one can change something without having to change everything else. And in that way, you can trust that if something like a top hash is still the same, then nothing has changed within that tree, or else all of it would have had to change. All right, and if you have a consensus from all the neighbors that you have within this network that this is what the top hash should be, then you know you can trust that that is indeed the top hash you should have, And if you now hash these bits of data and find the top hash is different, note that hash is actually changed. You can actually have a hash chain or a hash list, which is kind of a simpler version of this, where you're simply hashing something and you hash the hash of it, and you hash the hash of that. Okay, but you can look that up and it's interesting. Is it possible to have two nodes pointing to one node? P points to Q, Q points to R points to S, and then having G point to R? Yes, but then we no longer have a linear order. And what we're dealing with is not a list. Okay, we will get those types of things. Trees are one such example. Does the header and the trailer also contain an object, or are they just references? All right, so header will have null stored as its object, so it won't have an object there. Trailer as well, null. Header and trailer are actually references, so we better to put header above this and trailer above that. These are references to these Sentinel ones, but instead of an object, they store null pointers, so null. All right, but let's get into the nitty-gritty of it. So with thinly linked lists, we found that there was an issue. When we want to add something before, or we actually want to remove an arbitrary element, so not the first element, we want to remove any other element, including the tail element, then to be able to remove that node that contains an element, we need a reference to the node that occurs before it. And to do that, we have to link hop. And that isn't convenient because that is not constant time. That depends on the size of my list. If I have a list with 1 million nodes, it's going to take 1 million operations. That's not correct. So with a W linked list, we'll store two references, one to the next, as we did before, but now an additional one to the previous node, so the one that comes before it. They also contain central nodes, namely the header and the trailer, which are empty. Note, this isn't always the fact, it's convention. So we could give an implementation that doesn't have this, and you still need to be able to make it work. All right, so now how do we remove from the tail? Does it get easier? Yes, certainly. If we have a W linked list, then to remove the tail, we simply say, go to tail.previous, so one that occurs before it, which you now store a reference to, and update tails previous to point to the trailer. Then update the trailer's previous to point to tails previous. We have now worked the tail out of our list. We now update tail to point to the thing that comes before trailer. All right, the new last node. Adding at the head, well, it's simply adding after the header. Inserting in the middle, it's simply adding after some particular node. So we could define a single method, add after, and use that to define everything else. Inserting at the tail would simply be add after tail. Inserting at the front would simply be add after header. Inserting at any particular position would simply be add after that position P. Here we're given node V to add after, and we can easily add it after that. Just to clear some semantics, the word reference and pointer mean the same thing, or are they different? Okay, so in Java, we don't actually have pointers. Yes, we use references to refer to objects, that's how they're called reference types. So when I say pointer, I do mean a reference. Yes, when we're talking about linked lists, we'll talk about this link to a next one, but it really is just a reference to the next one. All right, and removing in the middle, again, it will be quite simple for us to remove from the middle. Let's take a look. All right, so now to remove P, I simply say p.previous.next, right? So I go to P's previous and I access its next, and I set that to p.next. That does that. Then I say p.next.previous, so P's next previous, and I set that to P's previous. Now this has fallen away, and this has fallen away. And because nothing refers to P, P should be collected by a garbage collector, and it's now removed. Usually I would store the element in some temp variable and return that beforehand, but that's effectively what we do. And note, I don't have to link hop to get to P's previous. I simply use the reference to it. All right, so it's now a lot easier for us to remove anywhere, not just at the beginning of our list. And there's some code that describes that within the text. For a W linked list, we now have this reference to previous and next. It's a nice way to implement a list. It's a natural implementation of the list ADT. Now our positions store not just an element and a link to the next node, but also a link to the previous node. We also have two special nodes that are called sentinel nodes, trailer and header, which are there to ensure that we always have something before and something after. I have a question here. So we set reference to null. No, we didn't set the reference of P to null. We simply had nothing refer to P. Yes, you could go ahead and say P.next is null and P.previous is null, but because nothing can refer to P, it will be collected by a garbage collector. Just think of, okay, most of you have done infos2b, and you may have discussed this in comsci2b. If I have on my web server a bunch of files, but some of them are not linked to by any page on that web server, then those files are known as orphan files. There's no way I can ever get to them. And so we have a server program that can get rid of orphan files, and you should do that regularly because those are files that are wasting your space. You can't ever access them because nothing refers to them, but they exist there. And so Java does a very similar thing. If nothing refers to an object, something that's actually stored within memory, then it will be deleted. Okay, and that's what happened to P. Once we take away the references to P, P's previous used to refer to it, and P's next also used to refer to it. We change both of those to not refer to P, and so P no longer has anything referring to it. If you do that, there won't be a problem. No, there'll be no problem. You can go ahead and do that. All right, so now this is what a W linked list would look like. We have double as many links, but we're now able to move freely in both directions. We could link hop from beginning to end, or from our tail back to our head if we wished. Right. Each of these nodes then represents a position, so it implements position. It has to have that method element that returns our element, but it also stores two references, one to the node after it and one to the node before it, known as next and previous. And you see here, we can store absolutely anything, right? Here we have these little animals that represent whatever is stored there. Our elements can be anything that we can define. So this is what a W linked list would look like before insertion. So we want to insert something here. Okay, we're inserting something or adding on something after P. All we have to do is create a new node. We store whatever that element is that we now want to store within our list. We update the previous pointer of this new node to point to P. We update its next to point to Q. Then we update P's next to point to Q, and why did that do that? Okay, that key should be above the other one. But in any case, we update Q's previous to point to this new node, and we now have that new node added after P. All right, so we just have a couple of minutes left, so I will leave it there and ask, does anybody have any questions? All right, so the ideas of a single linked list and a double linked list are not new to you. However, we see here now how we can implement a list ADT, so a new idea where we store positions in some order. We can store those using either a single linked list or a double linked list. Now, what we saw with the single linked list is that most of our operations were constant time. However, some weren't. we'll see it with the doubly linked list, we're able to get constant time execution for all our methods. And so it's a better way or a better implementation of our list ADT. So we have a question. If a reference to an object is lost, it can never be recovered. Well, yes, how would we recover it? Right? We have to have some reference to it to be able to create an alias, to be able to access its instance variables and methods. If we don't have that reference, then it's lost. We can't access it again. And so it should be collected by a garbage collector because it's just a waste of space. So this year we won't be having demonstrations on Eclipse. Well, during our practical lecture, anything that's of import I will show to you. But for these ones, your practical will be to actually implement these on Eclipse. All right, so usually what we'll have is that you have to implement some methods from the ADT we've been discussing, and then a main method within your main class that's like a driver class. It actually does something with that ADT that you've now implemented. All right. So in addition to removal, head and tail in W linked list the same is addition and removal. All right. Well, what did we see? We saw that adding to the front and removing from the front of a single linked list was constant time. It was really easy. We saw that adding to the end of a single linked list was easy. However, removal was difficult because we had to update the next pointer of the element or other the node that occurs before that last one that we're removing. So if we wanted to remove this one with a single linked list, it would have been not more difficult, but rather we first have to link hop to access Q, then we can remove this last node. Now we can access Q by simply accessing this current node's previous. So now removal from the head and the tail becomes constant time. So it's better in the W linked list than the previous one. How long is this class? It's a double, so it already ended at 9:35. That's why I stopped the slide and I asked if there are any questions. All right, so the class has officially ended, but I will just record the questions because they may be relevant to all students. Are these references to our list available for outside use? Ah, very interesting. All right. Well, would we want other classes to be able to access these? Usually, no. All right. It usually would actually want to only expose each position, which has a single method element, which returns the element. We wouldn't want to expose the node itself, because if someone has access to the node, and thus the references, they could destroy our list by simply setting one of those references to null. If at any point I break one of these, that will be bad. So it's very useful by defining a position and only allowing people to access those positions, even though they're implemented as nodes. If I only allow you to access position, you can only access the methods that are defined in that position interface, which are element. All right, so make the rest not exposed. Are the references auto-generated into memory? No, each time you add a node, the references are created, but they're set to default values of null. Either you can update them later, but usually we'll actually have that constructor that accepts the element and two references, and you would then use that to set the references to the previous and the next. Right, so we'll pick up from there tomorrow. I'll end our recording there.